Welcome back to Stats 2. In the lecture of today, we're going to talk about contrast coding again. As you remember from 2 weeks ago, we learned about how we can code categorical variables, categorical predictor variables in different ways, and how the choice of the specific contrast coding will affect the interpretation of the resulting estimates for intercepts or for slopes, right? And for example, we learned about treatment coding, which is like sort of the default or dummy coding that you will get in R if you don't specify anything else. Or we learned about sum coding, also the variants of it, like the normal sum coding or the scaled sum coding. We talked about repeated differences coding, or what else did we have? Helmet contrasts was another one. And finally, we also saw polynomial contrasts. And there are many more, okay? So I'm not going to write everything down. But one thing that we did 2 weeks ago was that we were always looking at these like already predefined contrast coding schemes that have some name, like treatment coding, sum coding, repeated differences, or Helmert. And we learned specifically about these categories, so to speak, and we learned in what way they affect, which hypotheses are effectively being tested by a model that is fitted using a categorical predictor coded by either one of them. Today, we're going to do something slightly different. We're going to take a much more general perspective, which is that instead of looking specifically at something that has already been given a name, like treatment or sum or repeated differences coding, we will try to see how we can, in general, find the appropriate contrast coding, which might be one of these or might be something entirely different, something that doesn't have a name, depending on the specific hypotheses that we are testing. Okay? So there is a procedure by which we can first define our hypotheses mathematically, and then we can calculate the exactly appropriate contrast matrix, like the entire scheme of contrasts we are applying, in a clear, straightforward way. And this much more powerful and general method of using contrast coding and choosing the appropriate contrast coding, that is what we are going to introduce today. So I'll show you what I mean using an example dataset from the LinkPsych package. So loading the LinkPsych package, we can access various example datasets. One of them is called df contrasts 2. Let's save that as a variable d, which makes it easier to access for us, less typing. And now let's see what this data frame looks like what kind of variables are in there. So there are 3 variables. There's one factor f with 3 levels. So we can also let R explicitly tell us what levels there are, how they are called. So there are the levels adjectives, nouns, and verbs. So it's sort of like a psycholinguistic study, I guess you could think of it like that. And there is another variable dv, which is some dependent variable, could be reading times in milliseconds, I guess. And then there is just the id, basically the number of the data points, which data point is it, the first one, the second one, the third one, and so on. Okay? So simple data set, one predictor, categorical, and one outcome variable, the dv, no hierarchical structure, so we don't have to worry about mixed effects or anything. We can fit a simple linear regression. But the interesting thing is now that we have these 3 levels, so this is already some complexity in the sense that we have to decide again how we are going to treat them. We can apply different contrast codings, and depending on which we apply, we're basically asking different questions, comparing these 3 levels in some particular way, okay? And so let me show you now how we can write down some specific hypothesis that we have, and then encode this hypothesis automatically using some mathematical procedure as a hypothesis matrix, which will then be converted into the optimal contrast matrix that we need, okay? Without even thinking about named concepts like treatment or sum or repeated differences contrast. Like we don't need those names anymore. We can just think of this general procedure going from hypotheses to contrasts, okay? So in the first example, let us do something simple, like let us use hypotheses that would sort of look like this. So I could say my first hypothesis or research question is, so okay, think of it as like a reading study where there are different reading times for different parts of speech, so like adjectives or nouns or verbs. And so now my first question could be, are the reading times of, or reading times, I'm considering this to be reading time, okay? It could be something else, I'm not sure, but it's an artificial toy data set anyway, okay? So are the reading times on the adjectives different, like either bigger or smaller than the reading times on the grand mean, like from the entire average over all three classes of words, okay? That could be my first question. And the second question could be regarding, well, I could pick one of the two remaining categories, so let me maybe ask the same question but about nouns. Like, are reading times on nouns either bigger or smaller, in either case not the same as reading times on like the overall average, okay? So this is one pair of possible questions I could ask here. There could be other questions I could ask. For example, I could ask about adjectives versus nouns and then nouns versus verbs. Or I could ask, I could ask different questions. But here I'm asking these two particular questions. Either adjectives are different from the grand mean, and the second question, are the nouns different from the grand mean, okay? And now let's see how we can represent these two questions, aka hypotheses, mathematically, okay? So obviously, this hypothesis, are adjectives different from the grand mean? I can transform it into a hypothesis, like first conceptually, by saying, okay, the null hypothesis would say that there is no difference. So the null hypothesis would say this should be equal, okay? That would be the null hypothesis. And the same for the second question. The null hypothesis would assume that there is no difference, that they are the same, okay? So if I want to write down what these null hypotheses are saying, just as simple mathematical equations, I could write the following. So if I abbreviate the class of adjectives as 1, let's say, and the class of nouns as 2, and the class of verbs is 3, just sort of to index different variables in the mathematical equation, I could then say, okay, my null hypothesis regarding the first question, so H0, 1, I guess, would be stating that the mean, which means the mean of the reading times, or whatever the dependent variable is, of the first group, the adjectives, that is equal to the grand mean. And so the grand mean I can just compute, assuming a balanced data set, of course, I could just compute as the mean of the three condition means, okay? So mean 1, mean 2, mean 3, meaning mean adjectives, mean nouns, and mean verbs, divided by 3, which will give me their average, and that will be the grand mean. Again, assuming that the classes are balanced, that they have the same number of data points, each of them. Okay, this would be my null hypothesis. And so by having this null hypothesis defined, I can now also deduce what the slope parameter is that I want to estimate and what it would mean. Namely, I could say, okay, I want to find some slope beta 1, which quantifies precisely the difference between the mean of the adjectives condition minus the grand mean, okay? And so my null hypothesis would assume that this beta 1 is 0, but it could also be different from 0, and that's what my linear regression will then try to estimate, basically, okay? Whether or not this is 0 and what exactly it is. So this would be the parameter corresponding to testing this hypothesis, or like possibly rejecting this null hypothesis more precisely. And this corresponds to our first research question here. The second research question would then yield analogously the following null hypothesis, so H02 maybe. So here we would assume that the mean of the reading times for nouns which is our condition indexed as 2 here, would be, so mu2, I could write, that would be equal to the grand mean, again, according to the null hypothesis, which says that there is no difference between the nouns and the overall average. And so again, just by analogy to what we saw here, we could then say that this corresponds to another beta parameter, another slope, which we can call beta 2. And this beta 2 would then quantify precisely the difference between the average reading time for nouns versus the average reading time overall. Okay, so I could write mu2 minus the grand mean, so mu1 plus mu2 plus mu3 divided by 3. Okay, so that is how we can represent these null hypotheses, these two null hypotheses as simple math equations. Now we'll further manipulate these terms here to get them into a specific form, which will then make it easy to see how we can create a so-called hypothesis matrix out of them. So that's what we're going to do next. So instead of writing beta 1 like this as mu1 minus the grand mean, I could equivalently, using simple math, also write the following. So I could say beta 1 is equal to mu1 minus a third of mu1, in other words 2/3 of mu1 minus a third of mu2, so minus 1/3 mu2, and finally also minus a third of mu3, okay? And I can do the same kind of re-expression of the same term analogously also regarding the second hypothesis. So here I could say that beta 2 can also be expressed in such a way of a simple sum of like coefficients multiplied with those parameters here, the mean, or the means basically, not the parameters. So I could say beta 2 is equal to, in this case, we'll start with mu1, so just minus a third of mu1, and then plus mu2 minus a third of mu2, so in short 2/3 of mu2, so plus 2/3 of mu2, and finally minus 1/3 of mu3, right, as we also had above, so minus 1/3 of mu3. Now, before we move on, let us now also think about an analogous way how to express the null hypothesis regarding the intercept of this comparison here. So for the intercept of this linear model, which we are going to fit, which is usually not so much of interest, but is still another valid like hypothesis that's being tested, we could analogously also formulate a null hypothesis. So we could say H0, 0 in this case, and this would now just concern the grand mean itself in this case. So we would say the null hypothesis regarding the intercept would say that the grand mean is equal to 0. So 0 is equal to mu1 plus mu2 plus mu3 divided by 3. And then likewise, we will also have the intercept parameter, beta 0, as we also usually call it, which we want to estimate, and this would then basically be just equal to the grand mean, okay? So we would say beta 0 is equal to mu1 plus mu2 plus mu3 divided by 3, just the grand mean, right? And again, this is something that we can also express here in this analogous way. So we could say we can rewrite this again as this simple sum of coefficient times basically mu something. And so here we could say beta 0 is equal to, well, what is it? 1/3 of mu1 plus 1/3 of mu2 plus 1/3 of mu3, okay? Now, the interesting thing we can do with these coefficients here, so 1/3, 1/3, and 1/3 for the intercept, or for beta 1, the first slope, 2/3, minus 1/3, and minus 1/3, and for the second slope, minus 1/3, plus 2/3, and minus 1/3, we can represent them as a matrix, okay? And this will be the so-called hypothesis matrix, also abbreviated as HC usually. And the idea is, okay, so let me first formulate this matrix. So, whoops, maybe I'll use this color again. So HC is equal to just this matrix, in this case a 3 by 3 matrix, where the first row will be with the values, populated with the values for my beta 0 for the intercept comparison. So 1/3, 1/3, and 1/3. In the second row, I'll have the values corresponding to this first slope, beta 1, so 2/3, minus 1/3, and again minus 1/3. And in the third row, I will have minus 1/3, 2/3, and again minus 1/3. All right? So the useful thing with this hypothesis matrix is that we can compute its generalized inverse, and for some very nice magical mathematical reasons, this inverse that we can compute in R, for example, using the G-in function, will be equal to the contrast matrix that we have to apply to test these exact three hypotheses. That's amazing, right? So we can compute the inverse of this hypothesis matrix, and this will be equal to our contrast matrix. Okay, so that is the useful general idea that we want to introduce in this lecture, that we can exploit basically, because that way we can first construct arbitrary hypotheses, represent them in this matrix form, compute the inverse of this matrix, and then we will get out the contrast that we have to use to like encode the particular categorical predictor in question. So let us see how we can define this hypothesis matrix in R actually. So here I have an R session running in the console, and we can, well, define a variable HC, and we could create this matrix using the matrix command as we've seen before, or just to see like a variation, we can alternatively also use the rbind, the so-called row bind command, which we can give a series of vectors where each vector would then be read in as a row for a matrix to be created. And the nice thing here with the row bind command is that we can also already give each row and like each entry in the row a certain label, a certain name. So we could say the first row is about our null hypothesis H00, which concerns the intercept, and this will contain the following values. So it will contain, for adjectives, it will contain the coefficient 1/3, okay, so 1/3. For nouns, it will contain the coefficient, again, 1/3, and actually the same for verbs as well, right? That's the first row of our matrix over there, which we're basically writing down in R now. As for the second row here, that is concerning our null hypothesis about the first slope, beta 1, H01, we could say. And this is now containing the following values, so 2/3 for the mean of the adjectives, minus 1/3 for the mean of the nouns, and again also minus 1/3 for the mean of the verbs. And the last row would then be, just by analogy, H02, where we would say adjectives are now getting the value minus 1/3, nouns are getting the value 2/3, and verbs are getting the value minus 1/3 again. And we can close the bracket here and create this matrix. Okay, so what we can do now is we can, well, first of all, just maybe sanity check that this matrix has indeed been defined as specified. So here we see it in the output of the R console. It's a bit less pretty now, obviously, because now it's in decimals, not in fractions. But in fact, if we load the mass package, there is a function called fractions, which allows us to also view decimal outputs transformed to the corresponding fractions, so 1/3, 2/3, and so on. So this looks a bit less cluttered, a bit more like nice. And one thing we want to do now also is to look at the transpose of the hypothesis matrix, okay? Just because then the rows and columns will have like the same layout or the same sort of corresponding categories as in the resulting contrast matrix. So that makes it a bit easier to follow. So let's also look at the transpose of the hypothesis matrix, again back transformed into fractions. So here we have this format now with now each row representing one of the levels and each column representing one of the hypotheses. So this is the transpose of our hypothesis matrix. Now, as I just mentioned to you, we can now compute the inverse, or in case of a non-square matrix, the generalized inverse, but which is also, like the generalized inverse for the square matrix is also the normal inverse. So in any case, the generalized inverse of this matrix, and then as a result we'll get out the contrast matrix that will correspond to testing exactly our specified hypotheses. And here, just to make it a little bit more nice, we're going to not use the ginf function, which we already know, but we're going to define like a new function which we can call ginf2, which gives us a little bit more nice output, and that it will retain those nice labels on the rows and columns. So you can find the definition of this alternative function also in the lecture notes, obviously, and you don't have to understand what the actual things do here that we write. So one thing is that we will want to have the output as fractions, and we will compute the generalized inverse here, which we can do using the ginf function from the mass package within our own custom function here. And so we're going to specify a further few things which are not so relevant. You can just copy paste the definition from the lecture notes basically. And this will be our function. So just computing the generalized inverse, but with some more like candy around it so that the output looks nice. So let's apply this ginf2 function to our hypothesis matrix. And we will save the result in a new matrix called xc, which will be our contrast matrix. So this is basically calculating the contrast matrix, okay? So let's do that, and let's see what our xc looks like. So our contrast matrix looks as follows, and maybe you noticed something. So just focus on the part here, the second and the third column, which correspond to our two slopes now, our two hypotheses. And this is in fact the same as sum coding. In fact, we just basically reinvented sum coding, right? If you remember how we defined our hypotheses, this was precisely the kinds of questions we would ask under sum coding, namely, is our level, for example, adjectives, different from the grand mean? That was our first question. And the second question was, is our level nouns different from the grand mean? Okay. And as we see here, if we specify the two questions as follows, then we will get on one of these artificial numerical predictors, like this second column here, we'll get a 1 for the level of interest, adjectives in this case, and likewise for the second artificial numerical predictor, we'll get a 1 for the new level of interest, namely nouns, and zeros if it's not the level of interest, and for the remaining level, the third level, which we never like ask something about specifically in one of the two hypotheses, we'll get a -1. And just looking at how sum coding works for a 3-level predictor, like in the textbook, you would see this, and it's not entirely obvious like where these numbers come from. But here we can see that just by thinking about our hypotheses naturally and then representing them as the hypothesis matrix, taking the inverse of that, we will get exactly these numbers. And so here for the first column, that is all 1, because that represents our intercept. And usually we can, like in the remaining examples that we'll see in this lecture, we'll like ignore this first column because it's always gonna, or should be always a 1 when we test the intercept. So this is sort of also part of the hypothesis matrix in the strict sense, like this row here, which will yield this this vector of 1s. But in the remaining examples, we can leave this aside and really focus on the contrast coding that we get out when we look at our hypotheses which concern some slopes, okay, like beta 1, beta 2, and so on. And just to really convince you that these two columns here are in fact identical to what the contrast matrix for sum coding would be if we just, try to get it from a default R function, we can do contrast sum for three level vector, and we will see that this will be in fact the exact same result, save for the first column on the intercept, which is omitted here because it's trivial. So the contrast coding for some contrasts is in fact exactly what we also computed by hand here. Like this is our contrast coding that we derived naturally, thinking of our hypotheses and then doing this matrix operation of taking the inverse of the hypothesis matrix. So if we wanted to get the same output from our manually computed contrast matrix with just these two columns, which represent the slopes of interest, we could do this. So xc and then index it with 2, 3 after the comma, meaning I want to extract the second and the third column, right? That would give me the same. And I could use this output now in order to recall that we still have our data loaded here, the data in the data frame D. And this is my factor of interest, like this predictor with 3 levels. I could now do contrasts of this predictor, and I could define them precisely as the second 2 columns of my manually computed contrast matrix, like basically assigning it our own customly generated sum contrasts. And once I do this, I can run fit a model as usual. So I can save it as fit sum coding, fit sum with the lm function. And I will say I have a dependent variable called dv in this case, and an intercept and a slope, which is specified as my predictor f, or in fact, as we know now, it will be actually now encoded as 2 separate slopes for 2 different hypotheses, for 2 different comparisons within this 3-level predictor. So anyway, my variable f, and I have to give it my data, which is stored in my data frame D, okay? And now if I extract the coefficients from this, I can see the result of that. So to keep it a bit short, I'll just say summary fit sum, and then just $ coefficients. And here we see basically the summary of the coefficients of fitting this linear regression. So the intercept, which represents the grand mean, as in sum coding is typically the case, right? That is 450 milliseconds, I guess, if we think of the dv as representing reading times. And oops, where did I go now? Oh yeah. And here we have the slope, the first slope regarding the first hypothesis, like corresponding to the question if adjectives are different from the grand mean. And so here it says that, yeah, indeed, in order to get to the level of adjectives, we have to go down from the grand mean by 49.9 milliseconds. Okay, so you can already deduct from this, like from this intercept together with this slope, that because this intercept represents the grand mean, that the average, the predicted average reading time for adjectives will be at 450 minus 49, so roughly 400 milliseconds, okay? And likewise, the second hypothesis was the one that compared the grand mean to the average of nouns specifically. And so here we have to expect this estimate, like under our sum coding, to represent the deviation going from the grand mean to the group level mean of nouns. And so here we can basically deduct, looking at this number together with this number, that the average for nouns, for the level of nouns in our factor here, would be 450 plus 49, so about like 500 milliseconds, okay? So basically output as we already saw it for some coding, with the only twist that we didn't have to like rely on some packaged sum coding contrast, but we actually created them ourselves by computing the contrast matrix by taking the inverse of our hypothesis matrix, right? So the rest is then all the same as what we saw previously. So this is all cool and nice, but it's still a bit tedious. Well, we have to admit to like define our hypothesis matrix by hand after figuring out what it should be, you know, as we did here on the board previously, and then manually compute the inverse, yada yada. So in fact, there is a package called hype-r, which makes this whole process a little bit more easy and intuitive to do. That's a package written by some people from Uni Potsdam as well. You can install it as you would do any R package using install.packages, hype-r. It'll take a moment, so I have to select some mirror from which I want to download it. It's really not important where I take it from. And after you've installed it, then you can load it using the library commands of library hype-r. Right, so here you can see that we also have thisginf2 function in there, but anyway, not so important. What we can do now is we can do the same thing again that we did before by hand, like figuring out what the coefficients are, but using a like automated way that this function provides us. So the way to do this would be to say, okay, I want to define my hypothesis matrix HC, and HC, and the way I'm going to define it now is by calling the hype-r function, like the same name as the package itself. And I want to now specify the first slope, which corresponds to my first like research question, beta 1 or B1, okay? And here I will now use the following syntax, like this is basically what the package provides. I'm now writing specifically, I want to compare adjectives, like the name of the level, against the grand mean, that is against nouns plus verbs, plus verbs plus adjectives divided by 3. Okay, that's how I would write it here. And then in the next line I could say B2, beta 2, that will be the comparison of what was it, nouns against nouns plus verbs plus adjectives. Okay, and then in the next line we would specify what our levels are in fact. So in this case it's noun, verbs and adjectives, or well actually it was in the correct order adjectives, nouns and verbs, so maybe let's stick to the original order that we had, and then we can close the bracket, and so we can create this, and let's verify what this HC is now. So as we can see, the HC, well, it's actually this object which already contains the corresponding contrast matrix as well. So once you let this be like given out to you in the console, you now see like this overall output, and here you have first a summary of the hypothesis matrix in the transposed form, where you have the 2 columns, which in the untransposed form would be rows, obviously, corresponding to the coefficients regarding beta 1 and the coefficients regarding beta 2, in regard to like the averages of either adjectives, nouns or verbs. And the contrast matrix would now look as we saw before. Just here it's also omitting the intercept column, which is kind of the trivial one. So moving forward we will like never actually explicitly look at the contrast for the intercept, but in principle you could like think of it just the same way, and it would usually be like this column of ones, but here we omit it again. But anyway, so the result here using the hype-r package is again the same. So we see that it's this classical contrast coding scheme that we would also get by default from this R function, namely that we have 1, 0, minus 1 as the first like artificial numerical predictor, which represents our slope beta 1, and then the second column would be 0, 1, minus 1, right? And so here we didn't even have to do the manual work of like defining the matrix by hand using these coefficients 1/3, 2/3, and so on, and then computing the inverse ourselves. But here we can just plug in basically what the comparisons are that we want to make into this hype R function, and then we'll get the rest out just automatically. So that's very neat. And so the proper way to now use this object HC, or what we've called HC here, but which is actually, you know, the output of running this hype R function, which is much more than just the hypothesis matrix, but also like the summary of the corresponding contrast matrix. In order to contrast code a predictor accordingly would be the following. So we would maybe again take our predictor F in the data frame D and wrap it with contrasts, and then we're going to define these contrasts as follows. So we're going to write contour.hypothesis. That's also a function from the hype R package, I believe. And then here we can give it now this object we've created with the hype R function, and this will be interpreted as assign the contrast matrix that comes out of this automatic computation to the factor in question, in this case F. So we can do this, and then we could also verify again that this indeed now uses the contrast coding that we've derived using the hype R function. And so we can just maybe appreciate for a moment that what we are doing here is still, okay, just sum coding. It has a name, but in principle, it wouldn't even need to have this name sum coding, and we could still derive the appropriate contrast coding scheme just by following this logic that we've introduced here, like creating the hypothesis matrix and then taking the inverse of that, which will give us the corresponding contrast matrix. So these were like our homemade sum contrasts, we could say. And now, as a next illustration of this idea and how we can use it very quickly and easily using this hype R package, we are going to see how we can create our own homemade repeated difference contrasts. Okay, so that's what we are going to look at next. So let's say we have a factor, for example, a 4-level factor, and we want to apply repeated difference contrasts, which, as you surely remember, means I am like, if this is like the first level, the second, the third, and the fourth, then I want to compare the mean of the first to the mean of the second, the mean of the second to the mean of the third, and the mean of the third to the mean of the fourth. So this is my first hypothesis, comparing levels 2 and 1. This is my second hypothesis, comparing 3 and 2, and this is my third hypothesis, comparing 4 and 3. Now, how would the hypothesis matrix look like? Well, let's think about it just the same way as we did before. So we could say our null hypothesis H0 for the first comparison to 1, that states that the difference between M2 and M1 is 0, or in other words, that M2 is equal to M1. mu2 and mu1. For the second comparison, likewise, I would say the mean of the third group is equal to the mean of the second group. And the next one would be that the mean of the fourth group is equal to the mean of the third group. And so each of these I can also represent equivalently as stating that, you know, mu2 minus mu1 is 0, or that mu3 minus mu2 is equal to 0, or that mu4 minus mu3 is equal to 0. And so in each of these cases, like, this difference is the slope to be estimated. So here in the first case, my beta for the first comparison, the beta for the comparison 2 minus 1 is exactly this difference, which the null hypothesis assumes to be 0. My beta for this comparison would say would be equal to the difference between the mean of the third and the second group, and the beta for the other group would be equal to, well, the difference between the fourth group's mean and the third group's mean. And now if we want to represent this, but like including all the coefficients also for the remaining means, which are not mentioned here, I could say, okay, in a slightly more detail, in each of these cases I could say, well, this is -1 times mu1 plus 1 times mu2 plus 0 times mu3 plus 0 times mu4, right? And likewise here, what do I have here? For mu1 I have 0, so 0 times mu1 minus 1 times mu2 plus 1 times mu3 plus 0 times mu4, and just the same thing now. Here we have 0 times mu1, 0 times mu2. We do have -1 times mu3, and we also got 1 times mu4, okay? So here in these equations, on the very right side, like in this part, you can already kind of see the coefficients that go into the hypothesis matrix. So like this -1, this 1, this 0, this 0, this 0, this -1, this 1, this 0, and this the same for the last line. So these numbers are our hypothesis matrix. So I can literally write HC is equal to the matrix which contains -1, 1, 0, 0, 0, just 3 rows. So 0, -1, 1 and 0, and finally 0, 0, -1 and 1. And so now the last step to get from this representation to the representation as a contrast matrix will be, as we just learned, to just take the inverse, the generalized inverse of this. So here in this example, we're leaving out the row for the intercept, which is always just 1. So in practice, we don't really need to think about it explicitly. The thing that we can do now is just go and say, what is HC inverse? That will be our contrast matrix. And in order to find this, we can conveniently use R. So let's do that right now. So let's find this generalized inverse of the hypothesis matrix using R, and then we will have our contrast matrix, which we can then plug into our statistical model in order to encode this categorical predictor with 4 levels in exactly the needed way, in order to have these like neighbor-wise, pairwise comparisons, the repeated difference contrast. So in our R script, or in the R console as I do it here, let's start by first defining this hypothesis matrix as we specified. So we could again use the rbind command, which allows us to give our rows and potentially also columns the particular labels we want to give them. So we can say first row will be about the contrast of the second versus the first group, and this will have the values for the first level -1, then for the second level 1, for the third level 0, and for the fourth one as well. That's the first row of the hypothesis matrix. Now the second row will be 3 versus 2, and here we will have for the first group a 0, for the second group -1, for the third group a 1, and for the fourth group a 0 again. Finally, we do have 4 versus 3, so here we'll have 0 for the first group, 0 again for the second level. For the third level, we have a -1 coefficient, and for the fourth one, we have a 1, right? As we saw here. So we can define this matrix, confirm that it looks as we want it to look. That's the same. And now we could also have a look at it in this transposed form, which we often do to have it like in the same format with rows and columns as the contrast matrix. So this is just the same thing, just now with the rows and columns transposed. And now we can just apply our generalized inverse function, our custom generalized inverse function, in order to compute the contrast matrix. If we don't want to define this genv2 function ourselves every time, we can also actually load the hypr package, which contains the genv2 function by default. So we can just do genv2 and then apply it to our hypothesis matrix. And this will give us the contrast matrix as a result. So compare, this is the contrast matrix, and what we had before here, this was the hypothesis matrix. So we could actually save this as xc, right? That's what we usually call our contrast matrix. And as you can see, okay, you see there's fractions here. So you have like -3/4 or like 0.075, and here you have like 0.25 and so on. You can see and verify that this is indeed the same contrast matrix we also get from the mass package, where we have the, I believe it's in the mass package, like conch as diff. Oh yeah, that should be in the mass package. Right, so if we do this automatic, like plug and play repeated differences contrast generation, where we just give this function from the contour as diff, like this function, our number of levels, we will see we get the same thing, right? This is the same thing now that we got manually. So if we would represent this as fractions, we would literally see that it's identical to our homemade contrast matrix, right? So that's what we got by hand, right? And here's what we can get using this like non-homemade function to generate our repeated difference contrasts. And the nice thing is that now we understand where these numbers come from. So 2 weeks ago, during the first contrast lecture, I just told you guys, okay, this is the contrast matrix for repeated difference contrast, just accept it. Like, we don't really understand very intuitively why it has to be these numbers specifically. But now we do, because now we know that these numbers, this contrast matrix, is just generated by this general formula, which, given the hypothesis matrix, which we can easily construct ourselves by reasoning through what the specific beta coefficients will be equal to, given our 3 comparisons in this case, we take the inverse of that, like the generalized inverse, because we have a non-square matrix, and then we get the contrast matrix as a result. So that is the full story here. We now know how these numbers, how they were generated. And now we also know the general idea of how to compute the contrast matrix for any set of hypotheses represented as a hypothesis matrix. As a last step to see that everything works, we could apply our homemade repeated difference contrast matrix to the example we saw already in the lecture 2 weeks ago, which is another of these toy data sets. In this case, it was DF contrasts 3, which contains this data on a simple data set with a 4-level factor. And we can now fit a linear model using our own contrast coding. So first, let's say we want to change the contrast coding of this F, which by now should still be the treatment contrast. I want to now change it to what my custom-made, homemade repeated difference contrasts matrix tells it. So we can verify that it has now really changed the values to the values we wanted to have for the repeated differences comparisons. And now we can fit the linear model. So we can say fit repeated difference contrasts should be our linear model that predicts the dependent variable dv. That's literally what the dv is called here, just dv. From an intercept and a slope based on, or actually 3 slopes for 3 different of these artificial numerical predictors we have now, like the 3 comparisons, 2 versus 1, 3 versus 2, 4 versus 3. Each of them will get a slope in this linear model, giving it the data that we had here. And we can see the summary of this. And now we see the same thing that we saw last time, that here we have now estimates for the differences of group 2 versus 1, like a difference of 10, the difference for group 3 versus 2, a difference of minus 10, and the group difference of 4 versus 3, which is again, which in this case is 30. Okay, just the same thing that we saw last time, only that here we gave it our like homemade repeated difference contrast matrix, which is like literally identical to the one we also get from the inbuilt R function, and we can convince ourselves that this works. Okay, we can create our homemade contrasts and then apply them to a categorical variable and run the linear model, and it will work just fine. Now let's try the same thing, but this time, as opposed to like writing down this matrix ourselves with the rbind command and ourselves doing the inversion, let's now use this hype R package, and literally the hype R package function, where we can do this very conveniently without writing down the matrices ourselves, and it should give us the same result. So just to sanity check, we could say we want, I'm again calling it HC, although now I'm not giving it just the matrix, but it's literally a more kind of complex data structure, which also will contain automatically both the hypothesis matrix and the contrast matrix in a way. So, but for simplicity, we're going to stick to the same variable name, just only that you guys like are aware of the difference here. And we're going to use this hype R function, and we're going to say beta 1, that should correspond to the comparison of F2 versus F1. Beta 2, that should correspond to the comparison of F3 versus F2. And beta 3, that should be describing the comparison of F4 against F3, right? And we give it our levels, which in this case are exactly these four. So in the following order: F1, F2, F3, and F4. And here we can see the same result, right? So here in this output of the object generated by the hype R package, we always get both the hypothesis matrix and the contrast matrix like in one go in the output. So we see that our hypothesis matrix is the same as here, well, just transposed, and we get the same contrast matrix out of it. And if we want to extract the contrast matrix and then maybe apply it to a linear model, we can do what we saw like a moment ago. We can do like a couple of moments ago. We can use this contour.hypothesis function, give it this object generated by the hype R function, and it will extract this contrast matrix, which we can then like feed into the definition of the contrasts of the particular variable we're interested in, and say we want to like give it this contrast matrix, and then, oops, what did I do now? Oh, it's called D, not DF. That was, of course, a mistake. Right, so now our contrast should be defined, well, as we also did it previously, but now we defined them by extracting the contrast matrix from the output of the hype R call, okay? Let's now apply the logic we have just learned so that we can create our custom hypotheses and then compute the appropriate contrast matrix from the hypotheses represented as the hypothesis matrix on a real data set. That real data set we're going to look at is called example3_syllables.csv. In my case, I've saved it in a subfolder called data. So I'm going to feed this into the read.csv command. You could find this dataset on Moodle as usual, attached to the lecture notes. In this case, the file uses semicolons, not commas, as the separator character. So I'm going to have to like specify this here as the sep argument. I can read this in and maybe save it as a data frame called D. Okay. Let's maybe have a look at what D looks like. So as you can see here, D has like these different columns, like it's an experiment basically, and the result of the experiment. So PPID is the participant ID, which like specifies which particular participant this data point belongs to. We have the item label, also like a unique identifier for the item. We have other not so relevant things for us now, like the position, the order of the trial. several other stuff. The main thing we care about are actually two factors, which are going to be our predictor variables. One factor is the syllable type, which I should have somewhere here. Oh yeah, so we have, or here it's called syllable frequency actually. So we have different levels of this. So maybe let's see what the unique values of syllable frequency are. We can see that it has the levels novel and HF, standing for, I believe, highly frequent. Okay, so there are these two types of syllables we might have. And this training type, aka exposure condition, as it's called here, has the following unique levels. So let's check that. Exposure condition unique. So there are three different conditions. In one setting, participants would be trained auditorily, like listening to these syllables. In another setting, they would be trained using production, like by having to produce them themselves. And the third setting is this control condition where I assume they didn't receive any training. And then there was like a subsequent task in which they had to like respond to syllables of such kind in some way. And this task would then record their response latency. Okay, so the response latency is just like the response time or time difference in milliseconds. And that is our dependent variable. So basically what we are interested in here is looking at these two predictor variables, two categorical predictor variables, one being a two-level factor, the syllable type, aka syllable frequency, and the other being a three-level categorical factor, the training type, aka exposure condition as it's called in the dataset. And those we want to basically look at as predictors of response latency, our DV, and find out if there is some meaningful statistical effect on either of them on the response latency. Okay? And so now the interesting task or problem regarding the contrast coding is how to encode each of these two categorical predictors. And this will, of course, depend on which hypotheses in particular we want to define about them. Okay, so that's what we are going to think through now. So, regarding the factor of syllable frequency, syllable type, this is a two-level factor, which lets us keep things rather simple. We might say that the null hypothesis, in this case, H0, I'm going to still call it H01, that will be saying that the mean, the mu for the novel syllables, novel, is equal to the mean of the frequent syllables, frequent or HF, okay, highly frequent, that's the abbreviation here, which in turn lets me define the slope to be estimated here as the difference between the novel syllable mean and the frequent syllable mean. So mu novel minus mu highly frequent. Okay? Or, well, there should be an equal sign here actually. So beta 1 is literally equal to the difference, mean novel versus mean highly frequent. Now, this is basically everything there is about my first factor, which is just a two-level factor. Recall that you can always just, or you have to specify exactly as many hypotheses as there are levels minus one. So for a two-level factor, you can just specify one hypothesis and that's it, okay? For a, like that's a two-level factor here of syllable type, the novel versus highly frequent. Now, for the three-level factor we have here, the exposure type, the exposure condition, we have the levels auditory, like AUD, control, and production. And so here we'll have to specify two hypotheses because we have three levels. 3 minus 1 is 2. And so the first hypothesis we might want to specify, like as a null hypothesis in particular, we can say H02. That should be about the difference between the production versus the control level. So mu of production, that shall be equal, according to the null hypothesis, to the mean, the mu for the control condition. So there's like no effect of training by production. That's what this hypothesis would be saying. And we specify beta here as beta 2, we can call it beta, will be equal then to that difference, right? So mu of production minus mu of the control condition. And we can do the same thing then for the third hypothesis. So that will say H03 is about, there could be different things we can do. In this case, let's again compare auditory against the control level, okay? So we'll say mu for the control condition. Oh, sorry, no, let's phrase it, let's write it the other way around. So mu for the auditory training condition is equal to mu to the mean response latency of the control condition, according to this null hypothesis. And so the corresponding beta parameter that's estimated here then would be equal to the mean of the mean of the auditory condition minus the mean of the control condition. So let's now use the hypr package to quickly compute the hypothesis and contrast matrix corresponding to this way of representing our two-level vector, and then also the appropriate hypothesis and contrast matrix for representing this three-level vector as we have specified using these two null hypotheses. Okay? So we're going to define our hypothesis matrix for the first vector, the two-level vector about the syllable frequency. And we're going to accomplish this using the hypr package as we saw before. And the single comparison we had just written down here was about the novel versus the highly frequent syllables, given those two levels, right? So once we have that, we could say, okay, let's create this. And here we can see how it will have coded our variables now. So highly frequent gets that's not the contrast coding yet, that's the hypothesis matrix. So in this matrix where we have the coefficients for the betas, we have a -1 for highly frequent and a 1 for novel. And taking the generalized inverse of this, we will get the hypothesis matrix, which is now scale sum coding actually, which is -1/2 for highly frequent and 1/2 for novel. Right? And in a way it makes sense that we get a scale sum coding out of this, because we did define beta here as, the difference between highly frequent versus novel. So highly frequent minus novel, or the other way around, like novel minus highly frequent. And that is exactly what we expect under scaled sum coding, right? That we want to have the coefficient beta to represent the effect magnitude, that is the difference between the two conditions. Now, actually, maybe let's save this hypothesis matrix object in a new variable called frequency, maybe, HC frequency, so that we can distinguish it from what we want to create now, namely the hypothesis matrix for the exposure type, or training type. So we'll do that the same way. This is about our three-level vector. And we're going to say the first beta, as we wrote it down previously, is going to represent the difference of the production condition versus the control. The second one is going to represent the difference of the auditory training condition against the control condition with no training. And we're going to say the levels here are the following three, so production, control, and auditory. So we're going to save that, and we can have a look at it. And this is what we see as a result. So the hypothesis matrix has these values with 1, 0 for production, 0, 1 for auditory, and -1, -1 for control. And the corresponding contrast matrix has these coefficients here with like 2/3 and -1/3 for production, for beta 1, beta 2, twice the -1/3 for control, and -1/3 and 2/3 for auditory training. One thing you might wonder about, maybe, is that, like, hang on, didn't we just actually encode treatment contrasts? I mean, just by the logic of the hypotheses, we compared two groups against the control condition, okay? That is very much what treatment contrast would do as well. So why on earth does our resulting contrast matrix not look something like, let's say, this, so with zeros for the control or treatment condition, and then a 1 for the production condition here, and like a 1 for the auditory condition here. That's what we would expect under the usual treatment coding, but here this looks different for some reason. Why is this the case? So the reason that this doesn't look exactly like our usual treatment coding as we would expect it is that using this hype R package, recall that we are always leaving implicit the slope beta 0 for the intercept. And now if we leave it implicit in this way of generating the hypothesis matrix and then the contrast matrix, then this procedure here will always assume that beta 0, the intercept, is going to be equal to the grand mean. So it will say beta 0 is going to be, in this case, 1/3 of the average of the first group, so production, and then plus 1/3 of the average of control. Like, it doesn't matter in which order you write it, of course, plus 1/3 of the average of the auditory condition. So this is the way in which this is different from the traditional treatment coding. So this is what we are basically doing here, okay? While when we have the traditional treatment contrasts, we are not assuming that beta 0 represents the grand mean, but in fact that beta 0 represents one particular group mean, in this case the control group mean, okay? So here you can see now why, depending on which hypothesis you make about the intercept, you will either end up with the traditional treatment contrasts, or you will end up with what we have here, which is these sort of treatment contrasts, but with the caveat that the grand mean also actually will represent that the intercept will also actually represent the grand mean. So this is just a thing to keep in mind when using the hype R package, that we are always by default assuming the intercept to represent the grand mean. If you wanted to see how we can get the traditional treatment contrasts manually, then you could obviously do that and define the full hypothesis matrix, which in that case would also include a column on beta 0, so it would be like the left column, which is implicitly left out here. So what we are doing in this situation is we are assuming that beta 0 will have 1/3, 1/3, and 1/3, right? These are the coefficients that we are making implicitly when we have the intercept represent the grand mean. But if we would take this and not define it as such, but instead would say, oh, the hypothesis matrix should contain coefficients 0, 1, and 0, meaning that there is a 0 coefficient for the production group, a 1 coefficient for the control group, and a 0 coefficient for the auditory group, which basically says, in other words, that the estimated beta 0, the estimated intercept, should represent the mean just of the control condition. In that case, if we take the inverse of this matrix, we will end up with something like this, with an additional column of 1s to the left. Okay, so that's something you could try as an exercise to confirm how this differs. But yeah, anyway, so what we can do now is we can take our computed contrasts, these ones here, and apply them to our factor of the exposure type, the 3-level factor, and we can also take our previously computed contrasts for the 2-level factor of syllable frequency and apply that, and then run a linear model with those contrasts specified as given here, and appreciate then what the output is and how we can interpret the resulting estimates for the parameters. So that's what we are going to do now. So let's say we create a linear model M, which we will do using the simple linear regression function. There's no hierarchical data here, so we are fine with just using simple linear regression. The outcome variable is the response latency in milliseconds. And to keep it simple here for this video lecture, we're just going to see the example where we fit two main effects. So we're going to look at the main effect of syllable frequency and the main effect of exposure condition using our data frame, which is saved in the variable d. So if we do this, so here I haven't specified the contrast yet. Here this would just use dummy coding, treatment coding, but we actually want to refit this model now using our contrast coding that we have computed here. So let's say contrasts of d syllable frequency, that should be equal to our contrast matrix. Oh yeah, we could do this command that we saw previously, contour hypothesis, and then we feed this our object we've created with hypr, so hc frac, that is our two-level contrast. Let's define this. Oh, okay. That's a small error here. We have to first convert our variable of interest to a factor. So here we have the syllable frequency. You can see if I load this from a text file, then by default, this is still just like a string, a vector of strings. So let's first convert this to a factor. So we can say d syllable frequency should be as factor d syllable frequency. And now we should be able to do what I tried to do before. So I've defined these contrasts. I can confirm that this has worked. If I access the contrast coding, I see this is my contrasts that I computed using hypr. And we can now do the same thing using our three-level factor here, the exposure condition or like training type. And the first step again is to convert it into a factor data type in R so that we're able to define contrast in the first place. So we're going to want to do that first. We could use as.factor to do that, or a very similar function is actually the pure plain factor function, which additionally allows us to define the order of the levels of this new factor. And the advantage of this is that way we can make sure that the order matches the order that we also used in the hypr call. Otherwise we might get a warning message or something. So we're going to say we want this to be the factor of this string column exposure condition. And here we have the second argument now, levels, in which we give it like our names of the levels as a vector of strings. So in this case, we should just make sure that it's consistent with the order of levels that we had in the hypr call. We had, I believe, production first, then control, and then auditory. So that's really kind of an arbitrary order, just the consistency is important. In hypr, we should have the same order as we have when we convert the factor to an actual factor data type in R, okay? So let me just check, everything looks as it should. So we can call this, and now just to see that this indeed did the trick, see this was the old output where both of these syllable frequency and exposure condition were still strings, like character data types. Now they are actually factor data types. So this is a factor with two levels, the syllable frequency, highly frequent and novel, and this is a factor with three levels, production, control, and auditory. Now we can go on and also define the contrasts of this three-level factor. So let's say contrasts of the exposure condition should be now assigned our contrast matrix we can generate from hypr, what we already did previously basically, which we had saved. So we had saved this object as hcexp, and using the contour.hypothesis function extracts the contrast matrix out of this object and assigns it as a contrast coding. So let's do that and see what happens. So we have assigned these contrasts. Again, we can sanity check if we get the contrast coding that we had seen previously, and indeed this is our contrast matrix, which kind of encodes treatment coding, but with the caveat that the intercept will still represent the ground mean. So we can now fit our linear model using the specified contrast coding, which we created using the hypr package. One small detail we still want to make sure is that for the particular research question at hand, like for this real data set, we are only interested in the trials where there was a correct response, which is indicated by this response variable having this value, this attribute correct. So as a minor step before we get to the actual model fitting, let's first create a sub data set, which we can call D correct. And this will now just contain the subset of values in D where the response is correct. Okay. So once we have that, we can sanity check what it looks like. Again, there's the same structure, only that here we are only left with the correct responses. And so among the correct responses, we now want to fit the linear model with two main effects, namely the syllable frequency and the exposure condition, okay, using the contrast coding we defined. So let's paste our model code back into here. And so we're going to fit this on D, sorry, not clean, D correct. And we can have a look at the summary and see what the results look like. So what we can see here is basically our usual linear regression model output. We have an estimate for the intercept, which using any contrast coding derived from hypr will always represent the predicted grand mean. Okay, so the predicted grand mean is 880 milliseconds, and it's significantly different from zero. That's the first hypothesis that this model is testing. And here we have our slope for the two-level factor syllable frequency. Recall that based on the coding we applied here, we coded the level highly frequent, HF, as -1/2, and the level novel as 1/2, which now means that we can interpret the slope estimate going from highly frequent to novel as follows. So as the increase in response latency for novel syllables compared to frequent syllables. So there's a 28 millisecond estimated effect magnitude in this regard. 28 because, well, 27.9, you round it, you get 28. And we have also this result of the hypothesis test. So we can see that on this parameter, there is this t-test result where we see that this difference is indeed significant. So there is an actual significant difference between the highly frequent versus the novel syllables and how quickly they are responded to in this experiment. Likewise, we have this slope, or these two slopes actually, for the three-level predictor based on the coding and the hypotheses that we have applied here in the earlier calls in hypr. And so here the first slope is about the difference between the control level and the production level. So going from control to production decreases the response latency by 26.6 milliseconds, meaning, in other words, that indeed having this training with production makes you more quick to respond to these syllables. And also we have a slope for the difference between the control, like no training condition, and the condition with auditory training. Here you have a decrease in response latency as well. The only difference being that the decrease for the production, comparison to the control, that was indeed significant. Whereas this smaller difference of just 10.5 milliseconds for the auditory versus control comparison, that doesn't reach significance here. So we can't really be sure that this is a real difference or just noise, but we can be somewhat confident that indeed this training based on production does in fact make a difference compared to a control condition with no training. All right, if you look at the lecture notes on the Moodle, you can find a few further variations of analyzing this data. For example, also including the interaction between the two factors, like the two-level factor syllable frequency and exposure condition. We won't do this here in this video lecture in the interest of time, but you can look this up in the lecture notes if you want. Now, the general picture that you should like take away from this second lecture on contrasts is that, well, before we had learned already about some like default contrast coding schemes that that are like easy to talk about because they are very common and have names. For example, okay, let's say we have a 4-level vector. I will now like represent each level of this vector as a dot. And so we already learned that like this most basic contrast coding that we can apply is treatment coding, where we pick one reference level, for example, the one to the left, and then we do 3 comparisons. We always do, remember, as many comparisons as we have levels minus 1. So we always do 3 comparisons. In this case, we compare this against the second level. We compare the first level against the third level, and we also compare the first level against the fourth level. So this is sort of the schematic representation of what has the name treatment coding, okay, or treatment contrasts. And we could do a similar schematic for what sum coding does. So we could say we have one level and another level, and let's again go with 4 levels. And here we'd say, okay, first of all, we compute the grand mean, or like the mean of all the level specific means. And now we compare this mean against each of these levels. So we would say, oh, we compare this against this, but also against this first level here. We would also compare it against the third level. Some contrasts basically. And we could also think about what Helmert contrasts are using this like visual idea. So we could say, oh, when we have 4 levels, then we would take the average of the last 3 and also the average of the last 2. And we'd say we compare, well, first of all, the last 2 against each other like this. Then we also compare the second level against the average of the last 2. And we also compare the first level against the average of the other 3, okay? So this would be what we typically know as Helmert coding or Helmert contrasts. And just one last example, if we have a 4-level vector and we want to compare always the neighboring levels, we have this comparison. So we compare the first one against the second one against the third, and the third against the fourth. That's what we are now familiar with already from 2 weeks ago as repeated differences contrasts. And so the general idea that you should take home is that these like schematic representations here, they have names, like these contrast coding schemes have names, but they wouldn't necessarily have to. And they are just particular, very popular examples like confined in this like small space of like contrasts which already have names that are like often talked about that we can use using built-in functions. But they are just, you know, examples from like this vast area of possible contrast coding schemes we could apply to a 4-level vector. And it might be the case that when we have some particular hypothesis of our own, or like, well, set of 3 hypotheses, that we are really not happy with either of these, but we want to construct our custom contrast. And this is the power we have now, because we now know how to derive any contrast matrix for any set of, in this case, 3 hypotheses about a 4-level vector. So we could, for example, say, oh, I'm really interested in doing the following. Maybe I want to compare always, like, let's say, the average of the first and the second level, the average of the second and the third level, as well as the average of the third and the fourth level. And then we'd say, because why not, that we want to compare the average of the levels 3 and 4 against level 1. We want to compare the average of levels 2 and 3 against level 2, and the average of level 1 and 2 against level 3. This would be a possible contrast coding that we could apply. It doesn't have a name, right? It is not a standard contrast coding like treatment, Helmert, sum, or repeated differences, but it works the same way. Like the main properties remain the same. We have 4 levels, so we do 3 comparisons between either like different levels or different averages of levels against some other level, or potentially even between averages. So that is like the power that we have now. We can compute, or we can like define any comparisons we want. Or like, to give you another arbitrary example, we could say we have another 4-level factor, and this time around we want to compare the average of level 1 and level 2 against the average of level 3 and level 4. And we also want to compare level 1 against level 2 and level 3 against level 4. That would also be a legitimate contrast coding. So you get the idea, I think. So we could continue this as much as we want. We can define our own custom contrasts based on our own custom set of hypotheses. And the nice thing is that we now have the power to just implement that very quickly using the hype-R package, for example. We could specify precisely this or an infinite number of other possible comparisons and just get like the corresponding contrast matrix with one enter pressing on the keyboard once we have the code for this. So that's very neat. We now are like beyond just simple well-known contrasts like the ones we saw 2 weeks ago. We're now capable of defining our own contrast coding with very specific hypotheses that we might come up with. So that's basically the takeaway from the lecture of today. Okay, I hope you enjoyed the material, and good luck with the homework assignment, and see you guys in the next video lecture then.